Similar to last section, we're still going to be looking at systems of equations, but instead of a system of two linear equations, now we're going to look at a system of equations in three variables. So it's going to be three equations, each in three variables, and I think we can be helped to visualize this by realizing that a linear equation in three variables is just a plane in three-dimensional space. So right now we're looking at the plane x minus y minus 3z equals -6. And every time we add an additional linear equation, we add another plane. So for instance, if I had a system of two three-variable equations, -x plus 2y plus 2z equals 1, and then this equation, you can see how whenever we manipulate the planes, they cross at a certain point, and specifically the way these planes cross is they cross in a line. So you can see the planes intersect each other at this line, and since these planes, they look like they're a finite object, but that's just to help us visualize it, they actually extend in all directions out infinitely large. So you can imagine these planes extending out forever, and they always intersect along this line. Now what can change is whenever you add a third plane. So right now these two planes intersect, but now we can visualize the third plane shown in blue, and do we see that while the blue and the green plane intersect in a line, the green and the orange plane intersect in a line, together they only all three intersect at the single point that we see in white in the middle. So the solution to the system of three linear equations in three variables, if the three planes intersect, they will all intersect at a single point here. Now, just as before, we could have a case where you've got three linear equations in three variables, but there happens to be no solution. One possible way that there could be no solution is if two of the planes run parallel to each other. So you see the green and the blue planes are parallel, they're never going to intersect. Now our third plane, shown in orange here, intersects both planes, but since all the planes don't intersect at the same location, there's no solution to the system. Because to be a solution to the system has to be a point of intersection for all of the items. So there would be no solution to this system of equations, because there's no place where all three planes intersect. Another way that we could see no solution is if all three of the planes happen to be parallel. So notice they never intersect each other at all. They live in separate sections of the three-dimensional plane. So there would be no solution here. And the third way that three planes could have no solution is where every pair of planes intersects each other, but no place has all three planes intersecting. So for instance, we can see that the orange and the yellow plane intersect, the orange and the blue intersect, the blue and the green intersect, but there's no location where they all three intersect. So this is another case of no solution. So whenever it was just two equations and two variables, we were a lot more familiar with visualizing lines, so it might have been a bit easier, but realize it's the same kind of situation for three equations and three variables. It's just now we're in three-dimensional space and we're dealing with planes. And the options are there could be a single solution where all the planes intersect. There could be infinitely many solutions if the three planes all intersect at the same line. So in this case, the dark green line that we're seeing is a point where all three of the planes intersect, so every point along that line is a solution. Or you could have no solution, and that could occur in a variety of ways. Whenever you have no solution, it's because the planes do not intersect each other all at the same location. All the planes could be parallel, so they never intersect. And each pair of planes intersects, but no planes all intersect at the same place. That's another case of no solution. So hopefully that helps us visualize what we're talking about when we're looking at that system of three linear equations and three variables. We are outside two-dimensional space and we're now in three-dimensional space. So that helps us visualize what's going on here. And in terms of finding the solutions, it's going to be the exact same process as before, just a little bit more time consuming because there's now more equations and more variables. So we can reference back here to help us visualize what we just saw earlier in our animations. One solution, infinitely many solutions because all three intersect in a line, and a variety of ways that you could get no solution. So let's go through our first example. In this case, we've actually been given a point in three-dimensional space. Now, we might not have seen three-dimensional points listed before. In two-dimensional space, there's just the x and y axis, but in three-dimensional space, you've got the x-axis, the y-axis, and then the z-axis. So whenever we write a point in three-dimensional space, x comes first, then y, and then z. So you can remember it's alphabetical. And we're asked to verify whether it's a solution to the system of equations. Now, similar, this is what we did when we previously were checking our work. What that means is we are going to substitute everywhere there's an x. We're going to substitute 6 into the equation. And we'll need to check that in each of the three equations. So each of the three equations should yield a true statement from this. So we're going to input 6 in for x, -4 in for y, 2 in for z in the first equation. We would get 6 plus -4 plus 2. Okay. Now that would give us 6 plus -2. That would simplify to +2 plus 2. That gives us 4. But what was it supposed to equal? It was supposed to equal 9. Now 4 is not equal to 9. So since there is one false statement, so this is untrue, if it fails for any of the equations, then it fails to be a solution of the entire system. So there's not even a need to check the remaining two. It's already failed enough. So we would say that the point 6, -4, 2 is not a solution to the system of equations. Now, had we gotten a true statement, then we would need to continue the process by checking the second equation and the third equation, and if they all gave us true statements, that's when it would have been a solution. So we saw what can happen if you're given a point, how to verify if it's a solution. But what if we're given a system of equations and we then need to find the solution, if there is one? The way you would go about this is quite similar to the last case, except you have to do a little bit of work at first. The first goal is to pick two of the equations to work with and get them down into two variables only. So the goal is to eliminate one of the variables and then do that again. So our goal is to eventually, through manipulation, get two equations in the same two variables. And once we have that, then we're going to solve that system of equations just like we did in our last section. And you'll get the value for the first variable and the second variable. Once you know those two, you can substitute back into one of the original three to find the missing third variable. So as you think through these problems, think your first goal is to turn it into a two variable and two equation problem. And from there, it's repeating a process that we've already practiced. So let's look at these systems of equations and try to identify what variable might be easiest to eliminate. Because while we could eliminate either x, y, or z, generally based on how the equations are written, one is going to be easier to try to get rid of than the others. Now, personally, I would try to cancel the x's, because do we see already the first and second equation, if I added them together, x plus -x would make the x's go away. So I could already get rid of the x's just by adding the first and the second. And then I could easily multiply the second equation by 2, and then add that to the third equation, and that would also get rid of the x there. So let's work through that. We're going to take the first equation, make sure as you write it down there's no copy errors, and we're going to add that to the second equation, no changes needed. Why don't you pause the video and add this on your own? Unpause when you're done. Now the x's cancel because they're exactly opposite of each other, and we would just be left with negative 2y plus 3y is a single y. 3z minus a z is a plus 2z. 9 minus 6 is a positive 3. Now I'm going to somehow mark this so I know to find it later. There's going to be a bit of work, so we'd want to try to stay organized. So that's one of our two equations that we were looking for. Now the next step is we are going to try to get another equations only in the variables y and z. The goal is to get two equations in the same two variables. And as we discussed before, I could multiply this second equation by 2 and then add that to the third equation, and it would nicely get rid of the x's again. So let's do that. Multiply this by 2. We know that 2 has to go to every term, both on the left and the right side. I rewrite the third equation unchanged because already the x's cancel as designed. And we would get y plus, in this case, 3z equals 5. Okay, so this is great. Now I have two equations in the same two variables. At this point, it becomes a problem very similar to our last section. You would solve to get one of these variables by itself, and you could either do that with the substitution or elimination method. I might say we could move this 3z over, and we would get y equals 5 minus 3z. So we can substitute this in for the other equation here. So that would give us 5 minus 3z plus 2z, because this took the place here. What that was equal to is equal to 3. Now negative 3z plus 2z gives us a negative z. 5 minus z equals 3. I'm going to add a z to both sides. And that would give me 5 equals z plus 3. Subtract 3. And we get that z would be equal to 2. Now as you work through these three variable equations, realize that the majority of your time is going to be spent just finding that first piece. And then once you have that first piece, it goes a bit quicker. So now that we know z is 2, we could use this equation to find y, right? Because if we know z is 2, then we would get y equals 5 minus 3 times z takes on the value 2. Y equals 5 minus 6, so y equals negative 1. Once we have that, we can now find the value for x. Now to find the value for x, you'd have to go back to an equation that involves x, which would be one of the original 3. Now you can choose to substitute values into any of these original 3. It's just going to be the one that you want to work with the most, and personally I think this one might be nicest to work with x. X is perfectly by itself. We could solve for it after we substitute. So x equals, or x minus 2 times now y is negative 1. Plus 3 times z is 2. That's supposed to equal 9. Negative times negative is positive. So we get x plus 8 equals 9, which we could subtract 8 from both sides, and we get that x equals 1. And this is great. We found the third value. So our solution, we see that this intersects at a single point. Our solution is 1, comma, negative 1, comma, 2, written in another format. And just as before, we can still check our work, except now we need to substitute this into each of the 3 variables and 3 equations. So let's start at the beginning. 1 minus 2 times negative 1 plus 3 times 2, that's equal to 1 plus 2 plus 6. That would be equal to 9. Let's check what was it supposed to be equal to. 9, the first equation works out. Let's continue with the second equation. Negative 1 plus 3 times negative 1 minus 2, that's equal to negative 1 minus 3 minus 2. That would be minus 6. What was it supposed to be? -6, that checks out as well. Third equation, 2 times 1 minus 5 times -1 plus 5 times 2, that's going to be equal to 2 plus 5 minus negative times negative is positive, plus 10, that's 17. It was supposed to be equal to 17, so that checks out too. So since it's a solution to each of the three equations, we know it's a solution to the system of equations, and we can verify that we got the correct answer. Now, our next example has the exact same idea. We're going to solve a system of three equations and three variables, except here we have the added twist where we have to come up with the equations on our own first. I'd recommend you take a moment to pause the video now and read through this example and attempt to come up with the equations on your own. I recommend you read it through once, get the idea, read it through a second time, try to start writing some equations, and then unpause and we'll discuss what equations we should write down to represent this situation. But do take a moment to read through and think about it on your own. So here we're told that three numbers add up to be 147. So sum up is the idea of this number plus this number plus this number equals 147. This is going to be one of our equations. Now we have more information. The smallest number is make us think of equals half the middle number. So that tells us how they're related, which is half of the largest number. And by the way this is phrased, they're talking about the middle number. The middle number is half of the largest number. So we're going to translate these piece at a time, but since we have things that are unknown, we need to be able to speak about those unknown things, which is why we give them variable names. And since they said there's a small, medium, and large, let's just say x is the small number, or I should say smallest. Y is the middle number, and z is the largest number. Next, let's translate each of these statements. So the first statement, the three numbers sum up to 147. That means if you take them all together and add them, you would get the value 147. So we've taken care of that first statement. Next it says the smallest number, what we call the smallest number x, makes us think of equals half the middle number. That's half of y. So we need to think about how we can make this equation. Take a moment to pause the video and write out the equation described here. Unpause to check your work. So we would phrase this, remember, x is the smallest number, so it would be equal to 1/2 times the middle number. X equals 1/2 times y. And that makes sense, right? Because y is bigger. So if you make y smaller by multiplying it by 1/2, that's what makes it equal to the smaller number. The options here would have been that or 1/2 x equals y, but this one doesn't make sense because it's saying if you make the smallest number smaller, you'll get the middle number. That doesn't make sense based on our labeling. So we've now explained the second sentence. Think about how you would write the equation for the third statement. The middle number is half of the larger number. That would be our middle number y is 1/2 times the larger number z. So we've translated each of the three statements and we now have a system of three equations and three variables. Remember, sometimes that bracket represents the idea that this is a system of equations. So if we are going to solve this, then our goal is to get down to a single variable. Now here, one thing I notice off the top of it is that x is supposed to be equal to 1/2 y. So what if I put in 1/2 y there, then this would be in terms of y, this would be in terms of y. If only I could write z also in terms of y, then this whole equation would be in terms of y and I could solve the problem. And I almost can. For instance, if I could get z by itself, then that would be z equals something in terms of y. And I could do that by multiplying both sides by 2. And we get z equals 2 times y. So let's substitute this here. That would give us the equation x takes on the value 1/2 y plus y itself plus 2y. All of that equals 147. This is great news because it's the same variable and we can combine this to a simpler term. This would be 3.5y equals 147 when we add them together. And when we divide both sides by 3.5, we would get that y equals 147 divided by 3.5. Y equals 42. So this is the first of our answers. And now what we can do is we can substitute to find x and z. Specifically, we know that z is 2 times y. So if y is 42, then z is equal to 2 times 42, which is 84. So that tells us z equals 84. Next, we can find x. We had the equation that x is 1/2 of y. So if y is 42, then x must be equal to 21. And now we can check our answer. Is this the right answer? Well, let's see. It's 21 plus 42 plus 84. That's 147, so the first equation checks out. Next, let's see. X, 21, is supposed to be 1/2 of 42. So we take 1/2 times 42, we get 21. The second equation works out too. So we've checked the first two. Now let's verify the third equation. Y is supposed to be 1/2 of z. So let's take 1/2, multiply it by the value 84 for z, and we get that y equals 42. So the third equation works too. So this is our solution, and if we wanted to write it as a single point, we would say the x value, the y value, and then the z value is an alternate way to write our final answer. Now we've discussed that a system of 3 equations and 3 variables could have no solution. We saw that visually, but how would you know that to be the case as you go about solving the problem? It's going to be similar to the 2 variable 2 equation case. As you go through solving the problem, eventually you would, through correct manipulations, get to an obviously false statement. At that point, you know the system has no solution. And it's going to be the same thing here. Now, as we begin to solve the 3 variable 3 equation, we know our goal is to get an equation, 2 equations in the same 2 variables. And do we see the second equation already is in terms of y and z? So that already is down to 2 variables. So I'm going to try to manipulate the remaining 2 equations to try to get rid of x, because then I'll have my second equation. So we need to think, how could I manipulate these two so that when I add them together, I'll get rid of x? Pause the video and think about that. Unpause to check your answer. We would want to multiply the first equation by -2, because since there's a positive 2x's, if there's a -2, then the x's would cancel, and I have to distribute that to each term. That would give me -2x minus 2y minus 2z equals -4, and we were going to add that to the third equation unchanged. When we add these, the -2's cancel as expected, and we would get -y plus 3z equals -4. Great. Double checking our work, everything's good. So now we have two equations in the same 2 variables. I'm going to write them near each other. And already, do you see I don't even have to manipulate these to cancel the y's. If I add these together, the y's are opposite, and they cancel. And perhaps unexpectedly, the z's also cancel because they're opposite. That leaves us with nothing left on the left side. Remember, when there's nothing left, there's a 0. When we add the right side, that would leave us with -3. But is 0 equal to -3? Definitely not. That's a false statement, which, since we did not make any mistakes, but we came to this false statement, that implies that there is no solution. So that would be our answer here. Because through allowable manipulations, we got to a false statement. That means these three planes never intersect. Now let's work through our last example of this section together. There are many ways that you could go about solving this, and depending on what you choose, it would make the solution possibly shorter or faster. So let's take a moment to try to plan and come up with what might be an efficient approach based on how the equations are written already. So one thing I notice off the top of my head is, do we see the z's in the first and the second equation are already opposite each other? Positive z, negative z. So if I just add the first and second equation as written, I'm going to get rid of the z, because my goal in solving a 3-variable 3 equation is to create 2 equations and 2 variables and then solve using substitution or elimination. So I'm going to add these together. It's helpful to rewrite it off to the side, that way you don't mess up the original equations. You need to be able to reference them later. Make sure as you copy you don't introduce any errors. So we're going to add these. As planned, the z's cancel. And we get 4x minus y equals 11. We're going to wait. We're going to come back to this idea later. Now we are going to go, our goal is to get rid of the z's in another pair of equations. So let's look back at what we started with. We already did the obvious choice. Next, I would say, what if we multiplied the second equation by what? What can we multiply the second equation by that when we add it to the third, the z's cancel? Would we agree if we multiply the second equation by positive 5, then as we multiply that through each term, we would get negative 5z that when you add to positive 5z would cancel. So we'll multiply that and we would get 15x minus 10y minus 5z equals 20. We can add that to this equation and we would get that the z's cancel. And we would get 16x minus 4y equals 44. So we have 2 equations in 2 variables. And we think about how would we try to get down to a single equation and a single variable. And one thing I notice is if I multiplied this equation specifically by a -4, wouldn't that make this into a positive 4y that you could add and it would cancel the y's there? So that's going to be my goal. I'm going to take a -4 and multiply it by that equation. So I'm trying to work the elimination method again here. This distributes to every part of the equation, left and right side. And we would get the new equation, negative 16x plus 4y equals negative 44. Now we're going to take that and rewrite it, and we're going to add it because we know that would help us cancel out our y's. And when we do so, not only do the y's cancel, but also the x's cancel. So we are left with 0 on this side. 44 minus 44 is also 0. Now 0 equals 0 is a true statement. So since we were solving the system of equations, we did everything correct, but we got down to a true statement of any type. 0 equals 0, 2 equals 2, anything that's true. that tells us that there are infinitely many solutions. So all our three planes intersect somewhere along the path of a line. So we would say infinitely many solutions is our answer. So hopefully we see the same procedure. It's very similar to the last section, except now we just have a third equation and a third variable. But the goal is to get down to two equations and two variables, and then solve those like we would before. And we have the same conclusions if we get down to a false statement or a true statement, or to a single point as our answer.